Alright, so now we're going to be talking about the equilibrium between solid and liquid. So the same thing happens if we're going to go from a solid where the molecules are pretty compact and close to each other to a liquid. All we're doing is making the distance further apart for the two molecules. So we're going to have to break those intermolecular forces that are holding those two molecules together. So that brings along the same sort of thing like the enthalpy of vaporization. There's something called the enthalpy of fusion, which is basically the energy it takes to take 1 mole of solid and to turn it into a liquid. Okay, so I went ahead and wrote the definition out for you. The enthalpy of fusion, basically the same thing as enthalpy of vaporization, but is the energy required to melt 1 mole of a solid and turn it into a liquid, and it's usually in kilojoules. So the units of this would be in kilojoules per mole. Same thing with enthalpy of vaporization. So that brings us to this right here. Here I have a molecule, which is methane, and I have the enthalpy of fusion and the enthalpy of vaporization. So the enthalpy of fusion is 0.84 kilojoules per mole, but the enthalpy of vaporization is 9.2 kilojoules per mole, which is a lot more than the enthalpy of fusion. But it does make sense, because if we compare the distance of two molecules, let's make these molecules red, get some color in here. So for a solid, the molecules are pretty close, okay? And this is going to be a solid. And then to turn it into a liquid, all we're doing is separating those molecules. Alright, well, it's about that distance for this video. So here's a liquid. So to go from a solid to a liquid, that will be the enthalpy of fusion, which is the energy it takes just to separate these two molecules. Now, if we were to talk about the enthalpy of vaporization, we have a liquid, so we'll make it the same distance as the one up there. So here's our liquid. And then we want to take it to a gas. Now, to take it to a gas, the distances between two gas molecules and two liquid molecules is very, very, very different. A lot further. So because of this greater distance that we have to separate the two liquid molecules, because of this greater difference, it's going to take a lot more energy. So the energy to take would be the enthalpy of vaporization. So because of the greater distance, we take more energy, so that's why the enthalpy of vaporization is a lot higher than the enthalpy of fusion. Now we're going to be talking about between a solid and a gas. So a solid can go directly to the gas phase, and this is called sublimation, and it can go reverse from the vapor to the solid, called deposition. And the same thing applies. We have something called the heat of sublimation. And there's something, and that's just basically the energy it required to sublime 1 mole of a solid. So to take 1 solid into the 1 mole of a solid into the gas form. So there's something cool about this, is that the enthalpy of sublimation equals the enthalpy of fusion plus the enthalpy of vaporization, which makes complete sense. Because if we were going to take, say we had a solid, and then we're going to take it to the liquid, right? And then we're going to take it to the gas, right? Okay, so to go from the solid to the liquid, we know that's the enthalpy of fusion. To go from the liquid to the gas, that's the enthalpy of vaporization. So say we have, of course, the same substance, and say we had 1 mole of solid, and then we're going to go to the enthalpy, or we're going to go take it to a liquid. So we would have to supply a certain amount of energy, in fact, which equals the enthalpy of fusion. And then to take that same liquid, we're going to have to take it to the gas, which will be the enthalpy of vaporization. But if we were to sublime it, we would go directly from the solid all the way to the gas. So if we were going to go from the solid to the gas, we basically have to take the same path as this, so we're going to have to use the same amount of energy as the enthalpy of fusion and the enthalpy of vaporization, because that is equal to the enthalpy of sublimation. So that's how the enthalpy of sublimation is equal to the enthalpy of fusion plus the enthalpy of vaporization. So now we come to this graph of temperature versus time. So say we took a certain substance, we could say water, and if we were to, or start with ice, and we were to gradually heat it up, we would get a curve sort of like this if we were to plot its temperature. So right here, we start as ice. So right now, let's do blue. We're in the solid. And then we continue to heat it up, heat it up, heat it up, and as time goes by, the temperature increases, and then all of a sudden, as time goes by, the temperature doesn't change for this certain amount of time. It stays constant. And this temperature right here happens to be, let's say, the temperature is going to be 0 degrees Celsius. Okay, so at 0 degrees Celsius, water freezes, or vice versa, the ice will begin to melt. So right here the ice is melting, but the temperature doesn't change. And the reason for this is that if we were going to talk about the molecules, well, we said before right here, the energy as we're heating it is going to be supplied to the solid water molecules. Then they're going to be vibrating more and more as the temperature increases. But soon, once we reach 0 degrees Celsius, the energy is no longer going to be supplied to vibrating the molecules. It's going to be supplied in order to break those intermolecular forces. So they're no longer vibrating more. The energy is being supplied to break the intermolecular forces, so the temperature doesn't change. And once all the intermolecular forces are broken, the solid is able to form into a liquid. So here we have the liquid. And then once again, as time goes by and we're still heating it up, the temperature is increasing. All that heat that we're putting into it is going straight into the water molecules, vibrating them more and more and more until it reaches this temperature, which you can guess what this is going to be. Say that temperature is 100 degrees Celsius. And once again, the heat that we supply is no longer going to be going towards vibrating the liquid water molecules. Is going to be to break those intermolecular forces in between the molecules so that they can free the liquid molecules and they can form and be released and form a gas. So here we have the gas. So you're probably going to see this. You're probably going to see this sort of graph, especially in one of your labs. But all you need to know is that these plateaus right here, the reason for the plateaus is that the energy being supplied into the whatever we're talking about is being used to break the intermolecular forces instead of vibrating or being supplied to the kinetic energy and vibrating the molecules even more and increasing the temperature. And then it can turn into a liquid, and once again it happens, the energy is no longer being supplied for the vibration, it's being supplied to break the intermolecular forces in between the molecules so that they can separate even more and become the gas. Okay, so that should conclude the videos on the phase changes. Everybody should be pros on the equilibriums between a liquid and a vapor, and a solid and a liquid, and a solid and a vapor now. I hope all this helped out, and if you have any questions you can send them my way and I can make a video on a certain problem if you have any requests.